Hi, thank you for letting me come to give this talk. And when I was putting it together, I realized in the spirit of this meeting that a pretty good subtitle is actually Exoplanet Hazes through the lens of Titan lab work, because everything I'm going to talk about today is very much predicated on a long legacy of lab work that's been done for Titan hazes to understand them. So, Julie talked a lot about this, but very briefly, if you struggle to follow any of that, very simply, haze is solid particles in the atmosphere that got there through chemical means. So that can be UV photons coming from the star that are impacting the atmosphere, breaking up those gas molecules, which reform into some sort of solid. More broadly, any sort of energetic particle that's impinging on the atmosphere can do that. And again, here I'm showing our favorite extremely hazy world, Titan. You can see beautiful haze layers kind of separating out high in the atmosphere then. And so that's an example of a very thick atmosphere with a lot of haze in it. But as Julie mentioned, we see these hazes across the solar system. So this is a picture of Pluto from the New Horizons flyby. And again, you see these beautiful haze layers forming, even though as compared to Titan's 1.5 bar atmosphere, this is an atmosphere of only a couple microbar. And haze is important not just because we see it everywhere, but it also can dramatically impact the atmosphere in terms of the temperature structure. So as an example, Pluto seems to be cooler than we thought it would be, and haze might be a really good explanation for why that happens. As Julie mentioned, it can dramatically change the bulk chemistry if you're starting to quench certain species down after that photochemistry has occurred. And finally, habitability is actually also an important consequence that comes out of haze production. Jod Arney's work has shown that hazes can protect the surface from UV that would otherwise be bad for life. But beyond that, my advisor, Sarah Hurst, has done Titan lab work again that has shown these very simple hazes that start to get made in the upper atmosphere of Titan actually start producing molecules we recognize as being important for life, including nucleobases and including amino acids. So not only can haze protect life, it can also maybe start making those building blocks. So that's all solar system. We expect haze to exist everywhere because we see it across our solar system, but we also have actual observations of exoplanets that tell us probably there's something going on there we have to understand as well. So I was talking to somebody yesterday and they said this is the most expensive flat line that we've ever gotten. And so those black points you see down there are Hubble observations, many Hubble observations of GJ1214b, which is a mini Neptune that it is, I'm gonna, I think, maybe upset Robbie here, but I like to think of super Earths and mini Neptunes as two distinct classes, where one of the one side of that is probably rocky and the other side does have a significant fraction of hydrogen helium. And this planet is distinctly on the hydrogen helium side. We would expect it to have a very volatile, rich atmosphere. And yet when we looked at it with Hubble, we see this flat line. So the top plot there you can see in yellow is what a pure hydrogen helium atmosphere would be. Clearly doesn't fit the data. But if you go to heavier gases like methane, water, carbon dioxide, they also don't fit the data. And yet we know that this planet has to have some sort of atmosphere. It's not dense enough to just be a solid rock. So it's telling you there's something else in the atmosphere that is causing an opacity that we can't see through. So a good candidate for that is either clouds or haze. So we set out to investigate this in the lab. And we did it by just trying to broadly sample some phase space that might be important because there are so many exoplanets, can't possibly do them all. So this is a set of equilibrium chemistry models actually that Julie ran for us to get our starting point. And what we did is we sampled 3 different temperatures, so 600, 400, and 300 Kelvin, so kind of the inner edge of the habitable zone and hotter, and then 3 different compositional regimes. So they roughly correspond to being hydrogen rich, so more like a mini Neptune, water rich, so this in-between thing that we don't really know what it is, and then a carbon dioxide rich atmosphere that is probably something more representative of being a terrestrial planet. And then up in the corner there, I also have our standard Titan gas mixture, which will become important in a second. This is what our laboratory setup looks like. So we flow all these different gas mixtures into this chamber here that I've highlighted for you, which looks like that when it's on. And we expose those gases to either a UV lamp or to a plasma discharge that initiates basically those chemical reactions to start breaking up those gas molecules and letting them reform into solid particles. Once we have the solid particles, we're interested in comparing them to what we already know. So again, I'm just showing you a bigger version of those initial gas mixtures. So I'm comparing Titan on the top to the two cooler water-rich atmospheres on the bottom. These are actual pictures of what the haze particles look like. And so you can see from these two water-rich cases, they're very similar in color to what we think of as Titan. And interestingly, they also made about the same amount of haze as Titan, which is not necessarily true. If I go back to this initial matrix, they varied in the amount of haze that they made by orders of magnitude. But these three are all pretty much the same. However, we then did combustion analysis just to get the bulk composition of the haze particles that we made, and you can see that they vary quite a lot, mainly in terms of the nitrogen and the oxygen. So these two cooler ones have way more oxygen in the solid products than does the Titan haze particles. So we wanted to investigate that a little further beyond the bulk composition, and so I did that by using very high resolution Orbitrap mass spectrometry. The particular instrument I was using required that I dissolve the solid particles in a solvent first. And this is sort of a lab science can be hard story. So you see in this picture here, maybe at the very bottom of that vial, you see all this black material. And that's because not all of the hazes were very cooperative in dissolving. And so I ended up making this chart of all the different things I threw at it to try to make the particles dissolve so I could get my measurements. And you can see it varies quite a bit. So I tried kind of progressively more and more heavy-duty organic solvents. But what was kind of interesting that came out of this is that all of the times that I did get something to dissolve, it's not going through, they ended up being polar solvents, and it skipped. There we go. So all of the polar solvents were somewhat at least effective at dissolving the haze particles. So first off, that's telling you that the particles themselves are probably polar. There's sort of a general rule of thumb in chemistry that like dissolves like. So the molecules themselves are probably polar. And more than that, and more than just for practical, I want to take my measurements reasons, this is kind of interesting because particles that are soluble are usually better cloud condensation nuclei. So this could be telling us something about the ability of these hazes to help form clouds. As an example, on Earth, to form water clouds spontaneously in the atmosphere, you would need a supersaturation of like 800%. That's not true on Earth. So clouds don't just spontaneously form even on Earth. They usually have some sort of initial condensation feed, like a salt or a dust particle that the water can then condense onto and start forming bigger cloud particles. So that's kind of a cool thing that came out of me just trying to take measurements. And then on to mass spectrometry. Maybe you're familiar, but if you're not, this is your crash course. This is a plot from actually the Cassini spacecraft when it flew through the plumes of Enceladus. So on the x-axis there, we have mass as a function of charge, and then intensity on the y-axis. And so each peak corresponds to a different molecule that we observed in that plume. So we can see methane and water vapor, and then progressively more and more complex organic particles. What I will really want to highlight here is that this chart goes up to 50 MZ. And also, the instrument that was on Cassini that was able to do this had very low resolution. It could only resolve one mass to charge, or one atomic unit. If we go to the measurements that I took in the lab, it starts at 50 MZ, and it goes out to 450. I actually took measurements out to 1,000. And you can see that there's a peak all across this chart. So first of all, this is telling you that this is made of very complex, very heavy stuff. And the other thing that I want you to notice is we see kind of this repeating stair-step pattern, which is telling us something about how these hazes are building themselves up. There are chemical families that are building where you're getting a repeating unit over and over again. Beyond that, things did pretty much every experimental condition we changed seems to matter. So this is just the hydrogen-rich hazes, or the hydrogen-rich gas mixtures. And so those top two were not soluble in anything I tried, and so I didn't end up analyzing them further, and you can kind of see they're a bit of a mess. But if you look at this bottom one, that's the one I just showed you, where you see this very nice kind of pattern pop out. And the only difference chemically between these different gas mixtures was this tiny sliver in green of ammonia. And so even though it's only present at like the 1% level, it's playing a dramatic role in the chemistry, how soluble this material is, and is partially telling you just how important tiny changes in the initial chemistry can be. I also compared the plasma source versus the UV source, and we generally see the same results. To move on to the water-rich mixtures, you can see all of them were soluble, and so you see really nice patterns pop out in each of these, but they also differ between the different mixtures. And so the first thing I did is add up the bulk composition of all of those mass spec data, partially to compare to what we got from the combustion analysis to make sure that my analysis was matching. But then again, to compare, I have all the way on the right here, Titan compared to those exoplanets. And again, just like we saw from the combustion analysis, all of them have far more oxygen than any of the Titan experiments that have been done. And you might say, well, obviously that makes sense. There's a lot more oxygen in those initial gas mixtures, but it didn't have to necessarily be incorporated into the solid. And yet we're seeing that, which is kind of cool. The other thing is this 600 in the box that I've circled has the most oxygen in the solid particles. It actually has the least oxygen in the gas mixture. But this is the only one of that particular gas mixture set that had carbon monoxide in the initial gas mixtures. And so it's telling you not only does the amount of each element in your initial atmosphere matter, the particular species that is a carrier of each element is mattering, because the carbon monoxide is much more likely to play in the haze formation process. I also was able to make specific molecular detections. And so we see all sorts of very interesting molecules in these haze particles. And we were able to see formulas for sugars, nucleotide bases, and amino acids. I mentioned at the beginning that Titan experiments have shown that you can make nucleotide bases and amino acids, but we have never seen sugars before from a Titan experiment. And sugars usually need liquid water to form, and yet in our just purely atmospheric experiments, we're seeing that we're able to make sugars, and it's probably, again, because of all this extra oxygen that is able to participate in the chemistry. And so just to quickly summarize, our exoplanet hazes seem to be polar soluble, which could be telling you something about their ability to act as cloud condensation nuclei. And so particularly for our atmospheres that are cool enough, this might be telling you something about water cloud formation on top of these hazes. This bullet point is mostly for the exoplanet crowd. For people who model exoplanet atmospheres, when they talk about hazes, they tend to just model hydrocarbon haze. And we're seeing that that is definitely not the only kind. Oxygen plays a very strong role. That will probably also change observations of what we can see. So it's important to know the kind of haze you're dealing with. And finally, we detect some very interesting formulas in our data from the mass spec of these hazes. And I didn't say before, but these are very much formula detections, and because we're not able to resolve structure with these mass spec measurements, and so we're gonna have to do some follow-up work to ensure that those are actually the molecules we're seeing instead of just a lucky formula that pops out of the data. And if you are very keen on lab astrophysics and lab planetary science, I'll plug a Chow Haze poster, which has more exoplanet lab haze, and then Michael Radke is also doing some Venus lab measurements. So thank you.
Thank you, Sarah, for that fantastic talk. And